Welcome back. This is video lecture 23.3, and we're going to talk about chapter 23, section 3, in which we discuss a charged, or I should say possibly charged, isolated conductor. Okay? And what we're really getting at, the key ideas in this section, are this. What are the general properties that we'll be able to count on being true? What are the general properties of any kind of conducting material in a condition that we describe as electrostatic equilibrium? What that basically means is that you have some kind of conductor and nothing's happening with it. If it's got some charge, a net charge of some kind, that's not moving around or anything like that. Just basically nothing is happening. Seems pretty boring, but it's pretty common with conductors. And so we need to know what these properties are, because we will need them a lot, because so many things are electrical conductors. So I'm just going to start with basically a laundry list of what are the properties of a electrical conductor in electrostatic equilibrium. First, we better define exactly what we mean by electrostatic equilibrium. I described it very loosely as nothing is happening, but here's what we really mean. That's the first condition here. Basically, the definition of electrostatic equilibrium. None of the free electrons or free charges in the conductor are accelerating. Let's remember what it means to be an electrical conductor. There must be in the body of the conductor a huge number of free to move about charged particles. Usually, those are electrons. Plain old vanilla electrons. Huge number of them, of the order of 10 to the 23, Avogadro's number. And they're just moving around freely in the body of the conductor. That's what makes it a conductor. If this conductor is in electrostatic equilibrium, then we mean that those free electrons in there are not accelerating. They're not being accelerated by forces. So that's just the defining condition for electrostatic equilibrium. And now come the consequences of making that definition. Here's the first consequence. Given the definition of electrostatic equilibrium, it must be the case that the electric field in the body of a conductor is equal to zero. Okay? I mean, that is worth writing. E equals zero in the body of a conductor. That is the first and foremost thing to remember about an electrical conductor in electrostatic equilibrium. There can be no electric field in the body of the conductor. Now, you ask, why? Simple. If there were an electric field in the body of the conductor, then there would be a force on the free electrons, right? F equals QE, and they would accelerate. Boom, no longer have electrostatic equilibrium. It's that simple, okay? So that is first and foremost the thing to remember in this situation. If the conductor is in electrostatic equilibrium, then there can be no electric field in its body. Now, next property. Let me try to be clear about this. Whereas there absolutely cannot be an electric field in the body of a conductor, that is not equivalent to saying that an electrical conductor can have no net charge. Charge and electric field are not the same thing. An electrical conductor could have a net charge, maybe because it was given some excess electrons. So it's got more negative charge than the positive charge from all the protons that it has inside its nuclei, and therefore the overall charge of the conductor is negative. Or maybe it lost some of its conduction electrons, so that it has fewer electrons overall than protons. Then it would have a net positive charge. Oh, it's definitely physically possible that a conductor in electrostatic equilibrium will have an overall charge that's not equal to zero. But if it does have a charge, there's something we can say about that, and that's the next property. If the conductor has a net charge, it doesn't have to, but it could. If it does have a net charge, this excess charge, right, the amount that's excess, must reside on the surface of the conductor, not within the body of the conductor. If the conductor has a net charge, that charge must reside, the net charge must reside on the conductor's surface, not inside the body of it. This we can prove from Gauss's law. Let's look at this little drawing here. What we've got is some odd-shaped sample of electrical conductor. It's a piece of copper, and it's hanging from an electrically insulating thread to the ceiling. It's that thread there, which is electrically insulating, that isolates the conductor from other things. Okay, so we have an isolated conductor, and there's nothing else happening to it, so it must be in electrostatic equilibrium. Let's say that we gave it an overall net charge of plus big Q. I want to prove that that charge plus big Q must be right along this surface, sitting right there on the surface. Okay? All right. Now, how do we prove that? Like I said, we apply Gauss's law. Remember, a Gauss's law involves a Gaussian surface, a closed surface. In this case, it'll be a mathematical surface that we can construct. It's up to us. The Gaussian surface, it's kind of hard to see in this 2D drawing, exactly mimics the shape of the conductor and is located just below the surface, infinitesimally below. Okay? So we have chosen this Gaussian surface to mimic the shape of the conductor, but be just below the surface. Okay? So we have a Gaussian surface just inside the body of the conductor. Now we apply Gauss's law to that Gaussian surface. The total electric flux, phi, I should say, phi sub E, through the Gaussian surface we picked, must equal the total charge inside that Gaussian surface over epsilon 0. Then what I did next is I just replaced the expression for the electric flux with basically its definition. Integrate the electric field, E dot dA, over the Gaussian surface. And the result of that integral must equal Q enclosed over epsilon 0. Okay. Now let's use property 2 that I just stated, that in the body of a conductor, the electric field must equal 0 everywhere. And the Gaussian surface is in the body of the conductor. So the electric field must be 0 everywhere along the Gaussian surface, since that surface is inside the body of a conductor. You see what I'm saying? That means in that integral of E dot dA, there is no E. And the integral of 0 is 0. So the electric flux on the left side of Gauss's law must be 0. There is no electric field to pierce the Gaussian surface. Well, if the left side is 0, then the right side of the equality must be 0. So the total charge inside that Gaussian surface must be 0, right? The total charge inside the Gaussian surface must be 0. Notice I'm not saying there isn't any charge inside the Gaussian surface. There can be charges inside the Gaussian surface. But in this case, the total of all that charge inside must be 0. Apparently, I must have just as much positive as negative charge inside this Gaussian surface. That's what the Q enclosed equals 0 means in this case. Okay, so there can't be any Q enclosed inside the Gaussian surface. Yet this conductor does have a net charge of plus big Q. The only place then for that charge to reside is outside the Gaussian surface. And since the Gaussian surface was just below the actual surface of the conductor, this charge plus big Q must be on the actual surface of the conductor. Okay? The excess charge on the conductor must reside outside the Gaussian surface, and since that Gaussian surface was chosen to be just inside the body of the conductor, the excess charge must reside on the surface of the conductor. Gauss's law proves it. Pretty neat, huh? All right, more properties to know about a conductor in electrostatic equilibrium. If the conductor has a net charge, again, it doesn't have to, but it could. And now we know that charge must reside on the surface of the conductor. That will, if this is happening, produce electric field outside. Not in the body of the conductor, but outside, because there'll be charge on that surface out there. Okay? That electric field that's created outside the body of the conductor must be perpendicular to the surface of the conductor at every point. So if I go back to this odd-shaped piece of copper up here, which we assumed had a positive charge plus big Q smeared out over its outer surface. That means the outer surface of that copper has positive charge. Then if I go around and sketch the electric field vector out in the outside space created by that charge, it's got to be perpendicular to the surface. Like that at that place. Roughly like that at that place. Roughly like that at that place. Like that there. Like that there, etc. You see what I'm saying? If it has charge, that's the first thing, then that charge must be on the surface. That's the second thing. Then that charge on the surface definitely produces electric field in the outside region where there's just air. And that field must be directed perpendicular to the surface of the conductor. Why, you ask? Let's talk about that. So my picture here, which is a bit rough, let me try to do a little better job. Up here at the top is trying to show the surface of a conductor. And I only drew part of it, but let me draw more of it. Okay? This is meant to be an electrical conductor. Okay? And we are saying that, suppose, there is positive charge smeared out over the surface of this conductor. It will be smeared out over the whole surface, of course. That will produce electric field in the air outside. But that electric field must be perpendicular to the surface at each location, like here. But over here, notice it's this way. You've got to be perpendicular to the surface at whatever point you're at. Like that, etc. Okay? We're going to show in just a minute that you can actually calculate what that electric field is using Gauss's law if you know one thing. What is the charge per unit area, sigma, on the conducting surface? Then you can calculate the electric field from this formula on the conducting surface, or just above the conducting surface. And I'm going to show you with Gauss's law how to calculate that. But before I do, let me explain how I know physically, because I still haven't really explained why, the electric field that points out into the air must be perpendicular to the conductor's surface. So here's another view down here of part of a conductor. There's the rest of it. There's the surface of it. Let's say it's got positive charge smeared out over it. And let's just pick a point like right there on the surface and ask what direction the electric field would have. Well, it's supposed to be perpendicular to the surface like that. But what if it wasn't? What if it was at a bit of an angle, like so? Notice that's not perpendicular. In fact, that proposed electric field has a component that we would say is tangential to the surface, along the surface, skimming the surface, and then a component that's perpendicular. The problem with this picture down here is that this tangential component of the electric field right there can exert a force on any free electrons that are on the surface, and that can cause them to accelerate. Boom, you don't have electrostatic equilibrium anymore. It's that simple. Okay? Okay, so these are the properties then. No electric field, assuming a conductor is in electrostatic equilibrium, properties are no electric field in the body of the conductor, none. 2, if the conductor is charged, doesn't have to be, but if it is, the net charge must reside on the surface of the conductor. 3. If there is a charge on the surface of the conductor, that charge creates electric field, not in the body of the conductor, but in the outside space. And that electric field must be on the surface of the conductor perpendicular to the surface. Now what I want to do is use Gauss's law to derive this result right here. The expression for the magnitude of the electric field at the surface of a conductor. I already know the direction must be perpendicular. Let's get the formula for the magnitude. And since it's magnitude, I really ought to have an absolute value there, because you can have a conductor where there's negative surface charge density on the outer surface. Okay, here is the scenario. Now what we're going to do is we're going to imagine we're looking at, let me get that down just a little lower there, a tiny patch, a tiny area on the surface of a conductor in electrostatic equilibrium that has a net charge that's positive. And we're going to zoom in on the body of that, on the surface of that conductor, so that this patch we're looking at looks flat. And the charge is spread out over it evenly. And that's what this picture on the right shows. It shows a kind of green shaded surface that's supposed to represent a small patch. No, that's not going to work if I don't get that down lower. A small patch of area on the conductor's surface. And this patch is described by a charge per unit area, sigma, in Coulomb per meter squared. That's the same at every point. That's what the little plus signs mean. So this charged patch is creating electric field, or there's an electric field at this charged patch, and we want to calculate its magnitude. We already know its direction. It's got to be perpendicular to the surface pointing outward. By the way, to the left of this patch behind here, you are inside the body of the conductor over here, and on the right side, you are outside the body of the conductor, okay? All right, in fact, now we're going to pick a Gaussian surface, and we're going to apply Gauss's law to the Gaussian surface and see what we can learn about the electric field. And the Gaussian surface is drawn here. I want to make sure you understand it. It's shaped like a kind of it's a cylinder, sometimes called a soup can, because soup cans are often shaped like cylinders. It's got a circular side, or a curved side, I should say, and two circular caps on the ends, the top and the bottom. Okay, and it's kind of sideways, and it's immersed so that it is straddling a small region of the surface, with part of the soup can extending above the surface and part of it below into the body. And the second picture here below is a side view, if that helps. Okay, to the left, we are in the body of the conductor. See how it's shaded green? To the right, we are in outside air, just shaded white. We see plus charge on the surface with the plus signs. We see electric field lines pointing perpendicularly away from this flat surface, like so. We see the side view of our Gaussian cylinder, kind of drawn in yellow. Okay, we're looking at the curved side, and we can see where there's electric field piercing that Gaussian cylinder. There is, in fact, only one place where there is electric field piercing that Gaussian cylinder. And I'll go up to the top view here. It's over this circular top cap, right there. That's where the electric field pierces. Here you see it, right there. At least one of the vectors is shown, piercing the top cap. If you think about the rest of that soup can and the way the electric field points, there aren't any other piercings. You see that? There aren't any piercings through the part of the conductor, the Gaussian surface, that's inside the conductor. That would be represented by this region, because that's inside the body of the conductor. And remember, the electric field is zero in there. There is no electric field to pierce that inside region. The electric field doesn't pierce this curved side on the outside right here. Here, because out there the electric field would just skim it on that side, doesn't pierce it. So the only part that gets pierced by electric field is that circular cap on the right. Now we're going to apply Gauss's law to that Gaussian surface. So phi electric equals Q enclosed over epsilon 0. And now we're going to start with the left-hand side. Which, remember, comes from integrating the electric field over the closed Gaussian surface. In this Gaussian surface, which is shaped like a cylinder, it's convenient to break this down into three separate integrals. The integral of E dot dA over the curved side, plus the integral of E dot dA over the left face, plus the integral of E dot dA over the right face. Okay? Now I've just made the argument that there is no contribution to the integral of E dot dA over the left face. Okay? That's over here in this side view, because there's no electric field there to pierce the surface. There's no E dot dA result from the curved side. Okay? The curved side of the soup can. Either because there is no electric field to pierce the curved side, that's if you're in the body of the conductor, or even if you're above the conductor in the region where there's air. Because on the way that Gaussian surface has been oriented, the electric field just skims the curved side there, doesn't actually pierce it. So all that's left is the integral of E dot dA over that right end. But that patch is so, that Gaussian surface is so small, I can make that Gaussian surface tiny, that the electric field is uniform, and it's in the same direction as the little dA, and you can do E dot dA there in the same direction. So you'll have magnitude E, magnitude dA, cosine 0, which is 1. So it'll look like that. And that area is so small that you can bring the E out front, the E magnitude, which I'm just now going to write as an E. And then you add up all the dAs, and you just get the total area there on that right face. Okay? And that's our symbolic expression for the flux. Now, the right-hand side of Gauss's law requires me to also think about how much charge is inside the Gaussian surface, Q enclosed. We've got to be able to visualize it in any given situation. Right? Once the Gaussian surface has been chosen and drawn, so we can see it in the picture, where is the charge that's inside? You've got to be able to visualize it. Do you see where it is in this case? Where inside this Gaussian cylinder on its side that straddles the body, the surface of this conductor, where is the actual charge that's inside? Where is their charge? Do you see where it is? It's right where the Gaussian cylinder pierces the very surface, right? On that circular region, right there. Because that's where the charge is, right? On the conductor's surface. So it's that circular cutout where the charge is. And that's the only charge in the whole Gaussian surface. There's no charge out in the air, and there's no charge in the body of the conductor. It can only be on the surface. Now, how much charge is it symbolically? Well, remember, we said that this patch of conductor is described by a surface charge density sigma, which we're going to assume we have figured out already. Remember, that's charge per unit area. So the total charge inside is the charge per unit area there, sigma, times the area of that circle I just drew, which is the same area as the circular end caps, A. And now I've got the expression for Q enclosed. And now I put them together in Gauss's law. Okay? phi electric E times A equals Q enclosed over epsilon 0 equals sigma A over epsilon 0. Let's divide both sides by A. That goes away. That means my answer that I'm going to get for the electric field does not depend on the area A of that circular cap on the Gaussian surface that we chose. Well, of course, the electric field, that's a physical phenomenon completely independent of us, can't depend on the property of a Gaussian surface that we pick. And so what you get for the magnitude of the electric field on the body of the conductor, on the surface of the conductor, is just that. Now it's technically, these are all magnitudes, so there should be an absolute value on that. Sigma over epsilon 0. Pretty famous result. Will be very useful. Okay? All right, I want to close the video by doing a little practice with you. I was going to have you do it as class engagement, but let's just do it together. Although I will recommend to you that as we go through this, you try to answer the questions yourself, pause the video, think about them before we talk about the answers. So we're going to practice with properties of a conductor in electrostatic equilibrium. All right, now, let's put a little twist on what we've been talking about. We've got a figure here that shows a cross-sectional view of a spherical metal shell. That's the thing that looks kind of bluish. And it's got an inner radius, big R. I don't care about its outer radius. And it has 0 net charge. Okay, now that's the conducting, it's called a conducting shell. That means it's electrically neutral. Neutral just means it has 0 net charge. Okay? Now, but that's not all. It's a shell, so there's a hollow interior, as the picture is implying. And somebody somehow put inside that hollow interior a point particle with negative charge in the amount of -5 microcoulombs, and it has been located a bit off-center. It's at a distance r/2 from the center of the shell. There it is. Okay? See, here's the center of that hollow region of radius big R, and our particle is a little over to the left by r/2 from that. Okay, that's the scenario. Now we're assuming everything's in electrostatic equilibrium, nothing is changing. Here's the first question. What is the net charge induced, fancy word, on the inner surface of the shell? And let's make sure we're clear what that means. Inner surface of the shell means the spherical surface just on that inside, right there. Now again, the picture looks like a circle, but remember it's a cross-sectional view of a sphere. Apparently, there is a net charge on the inner surface of the shell, and it's been induced, i.e. caused to appear, by what? By that charged particle in there. So we're going to have to find out how much overall charge is on that inner surface that I just shaded in green. And then I want to know if this charge is distributed uniformly over this inner surface. Notice we are talking about charge on a surface of a conductor. That's allowed. You just can't have any net charge in the body of a conductor. All right, how are we going to figure this out? Gauss's law for part A. We're going to apply Gauss's law. It's true for any closed mathematical surface we choose. To be useful, we just need to make a clever choice. I'm going to apply Gauss's law to a spherical Gaussian surface that is located in the body of the conducting shell. That's supposed to be a sphere. But the key thing is it's in the body of the conducting shell. Let me emphasize something now that I'll also emphasize in our class meetings. When we apply Gauss's law in our homework or on a quiz or on an exam, we, as the person solving the problem, have to draw in a picture somewhere where the Gaussian surface is, because we're the ones who pick it. And how is the reader supposed to know what it is if we don't show them? You have to show the Gaussian surface in your sketch. That's what I'm going to apply Gauss's law to. And of course, Gauss's law says the total electric flux through any closed mathematical surface equals the total charge inside that surface over epsilon 0. So let's start with the left side. The flux through the Gaussian surface that I chose, which in that 2D view is that red surface, which is shaped like a sphere, which is in the body of the conducting shell. So here's the first question for you. What is that electric flux through that Gaussian surface? Think about that a minute. Did you say the electric flux through that Gaussian surface is 0? Why? Did you say, well, you put the Gaussian surface in the body of a conductor. You can't have an electric field in the body of the conductor, so there isn't any field to pierce your Gaussian surface. So you did that yourself by choosing the Gaussian surface where you did. And that is correct. There is no electric flux through any Gaussian surface we might pick that's entirely in the body of the conductor. But then that means from Gauss's law that the left-hand side is 0. So we have to conclude that the right-hand side is 0. So the total charge inside the Gaussian surface, that's the red surface, or the one I've labeled, right, must be 0. Now that's the total charge inside. I'm not saying that there must be no charge at all. I'm saying there must be no total charge inside. Well, in fact, we already know we have a charge inside, right? We've got that point particle. Okay? So we already have -5 microcoulombs from that point particle. But the total's charge inside's got to be 0. There's got to be +5 microcoulombs of charge somewhere. It's not in the hollow region where there's air there, because there's just that one particle. It must be on the inner surface, the part I drew in green. Let's label that total amount of charge Q inner. It's the total amount of charge that's on that inner surface of the conductor. You can have charge on a conductor's surface. So 0 must equal -5 microcoulombs plus Q inner. Just solve algebraically for Q inner. And you get +5 microcoulombs. Okay? So there is +5 microcoulombs spread around that inner spherical surface of the shell. Is it spread around there uniformly, do you think? Evenly? What do you think? The answer is no, it is not, because of where that point particle is located with negative charge. Now I've got positive charge spread around the inner surface of the shell. There's going to be more of it over here on the left region, closer to the negative charge. Opposites attract. And there'll be less of the positive charge over here. Does that make sense? See what I'm saying? Now, what if that little point particle with negative charge had been placed exactly at the center, there, of the hollow region? You'd still have a total charge Q inner of +5 microcoulomb induced on the inner surface, but then it would be uniformly distributed around the surface because the point particle is at the center. You have symmetry going for you, but it's not. So that's our picture for part A. Okay? All right. Here comes another question. What is the net charge induced, caused to be, on the outer surface of the shell? And is this charge distributed uniformly over the outer surface? Apparently there's charge on the outer surface too. But wait a minute. What I do know for sure is that the Q total for this conducting shell must be 0. It's electrically neutral. We're told that. but I know that I've got charge distributed around that inner surface of that shell. So there must be also some charge distributed on the outer surface of the shell, so that the total is 0. Let's just solve algebraically for the charge on the outer surface. Well, it's just the negative of the total charge on the inner surface. Total charge on the inner surface is 5 microcoulomb. So the total charge on the outer surface is negative 5 microcoulomb. So if I go back to this picture, let me declutter it a little bit. Okay? All right. So the Gaussian surface is the one that's in the body of the conductor. The inner surface is the one that I drew right there on the inner surface. It has a total charge of plus 5 microcoulombs and is distributed non-uniformly over that inner surface. And now what we're saying is that there's also induced some charge on the outer surface of this conducting shell. You can have charge on the surface of a conductor. And that total amount of that outer charge is negative 5 microcoulombs. Do you think it's distributed around there uniformly? I will tell you one more bit of information that's usually implied in these problems, and it takes getting used to. Unless the problem says otherwise, you may assume that there's nothing else outside there except very far away. No charges outside. If that's the case, then there's nothing out there to perturb the charge on the outer surface, so it will be spread around. Let me try to do it evenly on the outer surface. Okay? And the last thing we are asked to do is make a sketch of the electric field line pattern in the following 3 regions. Inside the shell, in the hollow region, in the body of the shell, where there's actual conducting material, and outside the shell. So let me go back to the picture up here, because we're going to draw it on that. I'll draw them black. Okay, remember, electric field lines begin on positive charge, terminate on negative charge. They can curve if they need to. So what I have in the inner region, in the hollow region, is electric field lines kind of like that. See? Away from the positive charge that's on the inner surface, terminating on the only negative charge there is in there. Well, it has to come out perpendicular. Okay? On the negative charge. So some of the electric field lines in that gap region. Note that in the body of the conductor, right, where there's actual conducting material, there's no electric field at all anywhere in that body. E equals 0. So don't draw any electric field lines. That's a big point. And then outside, we have electric field lines that must be coming in straight, because everything's symmetric out there, from some positive charges that are way out there and terminating on the negatively charged outer surface, like this. Trying to make sure the electric field lines always come in perpendicular to the surface. Remember, they have to be perpendicular to the surface of the conductor at every point, like that. All right, so that's a sketch of the electric field line pattern for this conducting shell with a hollow interior with a particle in it, charged particle. There's a lot of good physics in that, and we'll be talking about that kind of stuff in class, okay, so that we can start to get used to these properties of conductors. That's all for this video.